Welcome to Lesson 5 in Colgate VizLab's Lessons in Autodesk Maya, a primer in particles. In this lesson, we're going to summarize the basics of working with particles systems in Autodesk Maya, specifically in the 2016 version. Now, in this lesson, you're going to learn what particle systems are, how to create them, and how each individual setting works and its general purpose. The purpose of this lesson is to give you a really basic idea of what particles are, and just how to apply them to a scene, how to maybe get started. The reason we're not going into more detail initially is because particles, like all visual effects systems, have a myriad of different uses. And so bringing them into Maya and into your scenes requires this primer before you get into more specialized use. I believe that this will allow you to get started with the basics, and if you run into a situation where you need to use particles, you'll be well versed in the initial systems and can therefore take them in a specialized direction. So, let's get started. To begin with, when you're working with particles in Autodesk Maya, you're going to want to set up your scene the right way. Now, there's a few little things that you can do that will allow your scene to be more receptive to particles and allow you to get the proper simulations going, etc. So, the first thing you want to do is make sure you're on the right menus. For the purposes of working in particles in 2016, you're going to want to be in the Effects tab up here. That's different from, for example, the Modeling tab, etc. And it'll change your menus up here. This will allow you to work specifically with end particles. Now, this being the initial menu that you use to instance things, and this here, the FX tab, kind of odd to have two, but if you want a more visual representation of the different tools at your disposal, here is that tab as well. The second thing you want to do, in addition to the menus, is you're going to want to make sure that your timeline here is set up the right way. Now, in order to do that, you're going to right-click on the timeline, which, as you guys should know, is just a representation of time passing in Autodesk Maya. Now, what you're going to want to do is look at the playback speed. Now, this is the most important part, just because when you play particles, the systems in Maya need to figure out exactly what they're going to do. They need to run calculations. They need to simulate the particles. Now, changing the playback speed will actually affect this simulation. Specifically, if you look here, you have three different options: real time, play every frame free, or play every frame max real time. Now, we're going to want this third option here, play every frame max real time, although you can, for the purposes of our discussion, use either one of the play every frames. Now, why do we want this? Well, specifically, you're going to want these because when you're simulating particles, you need to simulate the action of each particle on every frame. There needs to be no gap in that simulation, in that flow. Otherwise, if you run real time, for example, the particles themselves, when it becomes more of a complex simulation, it's going to try to evaluate them correctly and check every frame. So, for example, if you have, just by example, like a big torrent of flowing water, if you use that and play every frame when you're simulating, it's going to flow as your settings say it should flow. If, on the other hand, you have what's called play in real time, Maya is going to attempt to make a very as close to real time as possible simulation. That's going to allow it to skip some frames in your simulation, and you don't want that, because if you do that, it's basically going to screw with the flow of the water in our example there. It's going to make it go all over the place, go very wild, maybe too fast, maybe too slow. Either way, it's not going to be accurate. So basically what you need is either of these play every frames, because then it's going to simulate on every frame. That will allow you to have accurate simulations, and that's what we want here. So, to begin with, the basic way that you set up a particle system is under either this tab here, if you want the visual representation, or under the N Particles tab under the over tab Fluids, or rather not Fluids, FX, my mistake. So, to begin with, we're going to create emitter, and you can see here there's this tiny little symbol in the 2016 version. That symbol ought to match the symbol here. So if you ever are curious whether any of these match up with certain ones in the menus, you can have that visual representation there to sort of, I guess, just reinforce your memory. So we'll create that emitter. And when we create an emitter, you're going to see 3 separate objects pop up in your outliner. They are emitter, N particle, and nucleus. Now, these 3 particular sections are what make up a particle system. All 3 together combined, you can call that a particle system. So, what are these? Well, the emitter, the first thing we'll go over, is the actual place from which the particles come. It's the emitter. It emits particles. And when you're looking at the options, either in the channel box for the numerical representation or in the attribute editor for the various attributes and their sliders, this is the section you'll come to when you want to adjust how the particles behave as they spawn. This covers things like the way they emit, like different types of emitters. It covers the max and min distances from the emitter. It covers the direction they go, the speed they are when they start, etc. And they get a little more complicated from there. Next up, you have the N particle. Now, this is the representation of the particles themselves, and you won't actually see it here until we instance some particles. Now, you can see those spawning right there. That's just the basic flow of particles. And if I were to click on the N particle, you'll see that this box has appeared. Now, this box will always wrap around every single particle in that individual particle system. Now, this is going to go over a lot of different things, and it's probably the biggest section. This details what the particles are like after they spawn, how they interact with their environment, how long they last, how many of them there are in a scene, the size, the visual representation, whether or not they collide with objects, things like that. And then the third section we have here is what's called the nucleus. Now, this is probably the hardest to understand in general, but it's got the simplest explanation, kind of a paradox. But just let's simply say the nucleus is here to dictate the physics of the particle. So basically, it's going to dictate things like gravity, like the air density surrounding the particles, wind speed, whether there's a ground plane at all, independent of an object, which can be made a ground plane, which we can discuss later. It can dictate the, I guess, the detail in which the particle is simulated, and another few esoteric things, but essentially this is where you'll go to dictate the physics of the environment surrounding the particles. So, now that we've got those 3, let's start with the emitter. Alright, well, beginning with the emitter, we're going to take a look at some of the basic attributes here. The ones we're going to focus on today for the basics of your training are going to be the transform attributes, the basic emitter attributes, which is probably the most important section, distance and direction attributes, basic emission speed, volume emitter attributes and speed, and that's about it for today. So to begin with, we have the transform attributes. These are pretty standard across all different objects in Maya. Everything has a translate, rotate, and scale. Shear is a new one, which you'd have heard of the first 3, but not shear. Shearing essentially allows us to sort of do a smearing effect, a horizontal, vertical smearing effect on a emitter that has 3D space to it. That will only make sense for the volume emitter, which we'll get to, which is a specific type of emitter. But basically, that's just going to smear our little volume attribute there. Additionally, you have things like rotate order and rotate axis. That just changes the way you can transform or translate specifically and rotate your object. But it's not really necessary to deal with that, so we'll just focus on these first four here. So, I mean, as you can see, you can translate like with any other object. You can rotate it like with any other object. You can scale. However, when you reach the scaling, you will realize that you can't actually scale certain types of emitters. The only type of emitter that you can scale is a volume emitter, which again we'll get to in a moment. And same thing goes with shearing. You can only do that to volume emitters. So what are the different types of emitters? Well, you know one, it's volume. And the others we're going to cover today are directional and omni. Just to give you a basis of all of them, however, the directional allows you to spew particles in a specific direction, and you can adjust that through the distance direction attributes below. We have the omnidirectional, which, as you can see here, will spawn particles in a wide, basically in a sphere, in a 360-degree sphere direction. Now, you might ask, why are the particles not traveling in that specific direction or in a nova outward? Well, it's because under the nucleus, and remember the nucleus, we talked about physics under the nucleus has something called the gravity attribute. That gravity attribute, by default, is a 9.8. For anybody who is currently a physics student or has taken classes in high school in physics, you might remember that the standard gravity value is in fact 9.8. So we're going to neutralize that, bring it to 0, and now you'll see, zoom in a little bit there, now you'll see that the emitter, the omni emitter, is actually emitting in an omnidirectional pattern. That's what an omni emitter does. Now, something to note, we talked about translate and rotate and things like that. You might not be able to affect this omni emitter via rotation. However, you can affect it by translation. So you saw it was over here, you translated it, and it will actually change where your particles spawn. That's different than, say, moving the nucleus, which can be translated but won't actually do anything, and moving the end particle, which additionally will actually move the particle. However, if you generate it again, the particles will always be emitted and the end particle object reinstated here. So it's useless to move any of these. If you want to move where your particles come from, move the emitter. Moving on, we have the directional emitter. And as you might expect, particles from the directional emitter are emitted in a specific direction. In this case, by default, they are emitted on the positive x-axis. You can see down here, they are emitted along the positive x-axis. Now, how do we change that? Well, down here in the distance direction attributes, which directly relate to the directional emitter, you can see that direction x is at a positive 1 value. Now, that means that you're going to emit particles on the positive x-axis. If you want to change that, you can neutralize that, and in fact you'll get nothing. They'll just spawn on the origin until they disappear. Or you can increase on another axis to get, for example, the positive y direction, or even bring it to a negative value and get the negative of that axis. You can mix and match them as you like. You can even adjust them a little bit here, even while the particle is being spawned. Now that's generally a no-no. You don't want to touch your settings while your particle is being spawned and simulated, but you can, in this instance, do that. Now, additionally, you can add a little bit of spread to your distance emitter, or your directional emitter, excuse me. And that will, as you can see here, sort of add a cone-like effect And the more spread you give it, the more spray there will be. This is useful for things like a water spout or a flamethrower or something like that. If not, it'll just be a single line. The next type of emitter we have here is a surface emitter. Now we won't go into that too much, but suffice to say that a surface emitter is used for emitting from what we call a NURBS surface, or otherwise a polygon surface. It's just meant for emitting from geometry or NURBS. It's worth noting that unless you're undergoing some specific circumstances, you won't need to alter the emitter type to any of these. Instead, you'll end up going, I guess, for example, under the end particles and doing emit from object, which will automatically change your emitter to one of these and will allow you to emit from an object that way by default. So you don't really need to change it to any of those, and thus we won't really go much further into them. But suffice to say that surfaces do surfaces, curves do the curves here that you can create. That can be useful, certainly, but it's really not worth showing. Now, possibly, well, it's the last and possibly the most important emitter that we have here is actually what's called a volume emitter. A volume emitter has a unique property to all other emitters. You can actually change its size and its shape. That's very important for things like oceans, for things like galaxies, for things like, oh, you name it, a torch, an explosion, for example. Occasionally you need a multi-directional or multi-spawned explosion, for example. So as you can see here, there's this box, and by default the volume emitter is a cube. And you can see it spawns roughly from that cube. However, if you'd like to change that, you can go to the volume emitter attributes, and you can see that you have a number of different shapes: a sphere, a cylinder, cone, and torus. And that will allow you to change all of those. Some other side attributes here: you can offset the various X, Y, and Z attributes of that particular shape. So if you wanted to offset it from the surface a little bit in any specific axes, you can do that. Additionally, you can change the sweep of the volume emitter. You can change that primarily for ones that are circular or spherical, or in this case the torus. So currently it emits on a 360-degree spread. However, if you want to change that, you can see it's sort of like cutting a donut. You can make it a little more specific, so you can customize it in that way too. It's really, really versatile, and I find personally that I use this one and the Omni emitter probably the most. Additionally, you can change things like section radius, which scales things up and down. However, you can't change that with the sphere or the cube, or in fact any of the shapes other than the torus. So that's just primarily for the torus. However, what you can do is you can scale these, including the torus, in any direction you so choose at any time. So it's really, really versatile. I enjoy this the most, probably out of any of the emitters. So yeah, very, very adjustable. Another thing you can do with the volume emitter is you can modify the way it actually emits. So for example, let's get something a little more interesting, or a little more explainable. So you have this circle here, this sphere. It emits in a sphere-like pattern. However, let's say you want it to emit inward instead of outward. You would change away from center as one of the attributes. So now they still explode outward, however they, as you can see by the arrows, are being shot inward from this spherical shape. Now, additionally, you can do what's called along the axis, which takes the axes of the various shapes. See, there's the axis of the torus, and we had the vertical axis of the sphere, and it will allow you to add further direction to your emissions. Now, additionally, in addition to a long axis, we have what's called a round axis, which, as you can see, the axis of the torus is the loop. And I don't know if it can get you to see this. It's very cluttered. But you can see this arrow here. It's currently emitting around that axis now. Let's modify this a bit, just to give you an idea of what I'm talking about. Basically say not away from the axis, just around the axis, and a little bit along the axis too. So what you should get here is a sort of swirling effect. You can see it if you look close here. They're sort of swirling. In addition, they are traveling around it. However, they're, the physics of these particles, I don't know if you'd call that centripetal force, forces the particles away from it despite that. So you can change that. You can trap particles and things. But for now, that's just the modification you can make. Finally, you have what's called directional speed, which just modifies the basically just the speed in which they are moving based around their direction attributes. And then you have random direction, which just adds a random scale to any of the attributes here. And that's about it for volume emitters. For the most part, when you have a volume emitter, you'll be working within this section here. You won't actually be working with any of the distance direction or the basic emission speeds. Those are for the other emitters, and the volume emitter, when you have that out, you're pretty much going to live here. So that's basically all of the emitters tab. One more thing I suppose we can take a look at is the rate, which basically, you saw me scaling this up and down before. The rate pretty much just determines how many particles come out per second, as you can see here. That'll vary widely for whatever project you choose, so it just depends on what you prefer. So that is about it for the emitter, and in a moment we'll move on with the end particle shape. So the end particle node, as we discussed before, is a pretty sizable node. It's got probably the most settings of any of the visual effects nodes, and for that reason, I'm only going to go over the basics and the main areas that I feel you need to know to get started. If you'd like some more detail on this, I'm sure Joe can provide you a link to the Maya page or a digital tutors webpage that could show you the minute details of every little section here. However, I'm just going to go over these basics because I feel they are the functional sections that you need to most know to get started. So let's begin here. To start with, we have a section called count. Count is pretty simple. It just basically keeps track of the number of particles in a scene. Additionally, if you're doing things like caching or running a specifically timed event or something like that, you'll end up with a total event count in like a time-locked simulation, but otherwise you're just going to see this as the amount of particles in the scene at one time. Moving on, we have another section a little bit more important called lifespan. Lifespan basically is the amount of time from which a particle spawns until it dies, as they'd say, or just despawns or disappears. As you can see, we have a number of options here. Specifically, we have live forever, constant, random range, and lifespan PP only. Now, the three important ones are live forever, constant, and random range. This is because lifespan PP only is based around creating specific coded attributes for, or rather scripted attributes for particles, and we won't be covering that right now. And it's, unless you are scripting those additional attributes, it's not really necessary. So, to begin with, we have this live forever. Live forever is the default, and it basically just says from the moment you spawn your particles until the very end of your simulation, every particle that's spawned will exist forever. This is not really advisable for most simulations because A, it bogs down your scene, and B, a lot of times your effects will require a consistent amount of particles as opposed to an ever-increasing amount. So that's up to you, but the most constant use, the most frequent use will be constant. Constant allows you to set a lifespan in terms of seconds. So you have lifespan there. And you can see particles spawn, and about a second later, it could be 24, it could be 30 frames, depending on your seconds, later, it disappears. Pretty straightforward. The next one is random range, and what random range is it is constant with a variable. So you have the constant lifespan up top here like before, again in seconds. However, you can set a random range, and what that means is that you can specify a variance in your constant lifespan. So basically you could say lifespan like 3 seconds with a variance of 2 seconds. That means that every particle that spawns will stick around between 1 second and 5 seconds because it's a plus minus of 2 seconds. So that's just the variable there. That's useful in making your simulations a little more organic, and I like to use it for a lot of different things like that. So something that we'll expand on a little bit later is going to be particle size. But just to give you the basics of particle size, for particles that are not simply dots like we have here, you will need to use particle size to increase their radius. The next section that is important is going to be collisions. Now, collisions are very important because they essentially allow your particles to interact with the environment. Collide and self-collide, the two checkboxes up top, basically say, does your particle collide with the world around it? Yes or no. Self-collide means, does your particle collide with other particles in the same box? Yes or no. Pretty straightforward. Additionally, you have the strength with which they collide, which basically says, do they hit firmly or do they hit softly and sort of mush against each other? Do they lose any inertia from their collision? That sort of thing. Collision layer creates a sort of buffer around the object and sets the value for that buffer in terms of radius. Basically says, is there a thickness to the level of collision? Like, is there if there's a 2 foot sphere, is 6 inches of that part of the collision, or is it not? It allows you to create an extra layer buffer on top of that. Additionally, you have a collide width scale that allows you to scale that collision layer. Same here with the self-collide. It's just focused around particle to particle as opposed to particle to world. Bounce allows you to basically create particles that have a spring to them. So this is particle-centric as opposed to environment-centric bounce, which basically means each particle has data in it that says if it hits a surface, it will bounce a little bit before coming to rest in the event of gravity. Friction allows a particle to lose more or less inertia when it collides with an object or itself. Stickiness is pretty much the opposite of bounce, in which case it will try to stick the particle to whatever object it's thrown at, more or less depending on the value here. And finally, we have max self-collide iterations. That basically says how many times can a particle collide with another particle in the same box before it no longer does that. That can be useful to limit the number of collisions in the event of a huge field of particles, which would otherwise bog down your processing. The next important section I'm going to give you guys is dynamic properties. Now, dynamic properties basically give you a number of different influences on your particles. Local force will allow you to push particles consistently in a certain direction based on axes. For example, let's say there is a force on the x-axis. Here's our x-axis. And you see there's that local force. Now let's say I don't like that x-axis. I'd rather they not do that. How about the y-axis? The positive y-axis. And there they go. Very straightforward. Wind does a similar thing. However, there's a slight variance in the force provided. And as you can see, there's a slight turbulence to it, which can be adjusted in the various wind settings. So it's a little more versatile. Additionally, although I can't quite confirm this off the top of my head, but I believe wind is affected differently by things like gravity. So just something to look into rather. Moving forward, we have something called dynamics weight. Now what dynamics weight at a default of 1.0 does is it changes the amount of influence your dynamics, like force and wind and drag and damp and things like that, have on your particle set. If it's a value of 0, things like that will have no effect at all. And if it's a value of 1.0, which is standard, they'll have 100% of their effect. So it's just a sliding scale for you. Conserve basically controls how much of a particle object's velocity is retained from frame to frame. Put in a more specific way or a simpler way, conserve basically says how much velocity is retained as it moves through space, how much speed is retained. Conserve is at a 1.0, which means velocity is going to be conserved and subject only to other forces. However, if you scale that down, the velocity conservation will scale down accordingly. Drag and damp are two that are fairly similar. However, drag specifies the amount of drag applied to the current end particle. Basically, it's aerodynamic force parallel to the relative wind, which causes resistance. Damp, by contrast, is the amount of motion of current end particles are damped. Damping basically, like Maya defines it as, damping progressively diminishes the movement and oscillation of particles by dissipating energy. Now, what do those definitions mean? Basically, drag allows your particles to slow down and lose momentum in the face of wind and other effects. Damp works independently of other forces and just dissipates the energy that a particle has when in motion. So they're a little bit different, and they have some fairly specific uses later on. Depending on what your goal is, you'll use one or the other or both. It just depends on how you want your particle to behave. And then finally we have mass, which is basically just the mass of your end particle. Mass determines the density or the weight of a particle, and only affects the particle when the gravity value, you remember that from the nucleus, is greater than 0. And it'll just change how much mass an object has, so it'll make it more or less affected and lighter or heavier in terms of its relation to gravity. So that is dynamic properties. They're a little esoteric, but they're fairly simple to use once you get a little practice in. Again, particles are very goal-based, so using one or the other will be up to you depending on what sort of behavior and effect you're looking to achieve. The next important section that I'm going to go over with you guys is called shading. Shading is where you'll basically determine what your particle looks like, at least pre-render and as well as during render. The particle render type is probably the most important part of this section, as it can allow you to switch from the default point something called multi-point, which is clusters instead of single points. Multi-streak, which is a series of streaks. It may look blurry there to you. Streak itself, which is just the streak equivalent of point. So there's streak and point, and then multi-streak and multi-point. Same concept. Then you have numeric, which assigns a numerical value to every single particle. I'm not entirely sure what that's based around. It may be random, or it may be based on lifespan. Spheres are one particle that like we discussed earlier, can benefit from the radius value. That's what you'll use that for. Sprites, which you can't see here, will allow you to import pictures and apply them to your particle shapes. That's useful for things like textured particles, which can be a lot of fun. Blobby surface is very similar to spheres. However, if you increase this amount, when it's rendered in a certain way, the particle will look like sort of a slime splash, because the particles where they collide and where they self-collide, more specifically, they will sort of merge and form this blobby surface. We also have cloud, which is fairly self-explanatory, and tube, which is independent of camera movement. However, if we adjust the radius up top here, or not, well, ideally, you're going to get a series of tubes that, as you move the camera around, will align their orientation to the camera movement. Not sure why they're unaffected at the moment. I'm not sure if that's a bug, but regardless, the most important ones for you guys are going to end up being multi-point, multi-streak, points, spheres, and streaks. Occasionally you will use clouds as well, and once in a while maybe the blobby surface, but those are your most important ones. I say this primarily because a lot of the time what Joe will have you doing here at the Viz Lab is working on things that are astronomy based, for planetarium shows and things like that, and creating fairly conventional effects like fire and water and things like that. So when you use particles for that, you're going to want to start with the ones that I've shown you, the fairly basic ones. So now moving forward, here's what I was missing with the tubes, by the way. They can be shaped and changed there we go. There's your little tubes based around radius 0 and radius 1. And now, as you see, as I flick through these, each will have a variety or none of these options available. Like certain ones like multi-point will have the multi-radius where you can increase them. You won't be able to find that in standard point and streaks, but you'll have that in multi-point and multi-streak. Line width, for example, works on multi-streak and streak, but not on point. Stuff like that. So feel free to dig in here. This is one of those sections where experimentation is going to help you guys out a lot. So feel free to dig in here and figure out what specific particle type works for you and what options work for you in terms of customizing. Customizing. And finally, the last important one that I'm just going to go over is the time attribute. And I say it's important, it's more just a staple, a static frame in your node here. So basically, the time attribute is here to show you what your start frame is for your simulation and the current time in frames that your simulation is at. Now you can modify those later. However, here it's just for observation's sake. So, yeah, that's basically the emitter, or rather, I'm sorry, that's basically the end particle. And from here, we're going to move to the nucleus. Now, here in the nucleus node, we have a few different applications here, not too many, and most of them are fairly practical and useful. It might be a little harder to understand the science behind it, however, the applications are pretty practical and easy to use. So, to begin with, we have our probably the most obvious physical change in particles here, the force of gravity. Now, gravity, as we've said before, is at a default of 9.8 when you begin. That will allow you to see. Now, if you recall, we had a slight wind force active on this particle. Now you can see that that force is still active, however, gravity is the current driving force here. And the wind is just interacting with the particles in addition to that gravity. So you can see that there. You can increase the gravity, and you're likely to see that force, it tugs more on that particle. Alternatively, you can neutralize it or create a negative force of gravity, which creates that falling up effect. To achieve the same thing, you can use what's called gravity direction. Again, pretty self-explanatory. However, it basically says pick an axis and pick the amount with which gravity is affecting that axis. So you have a negative 1.0 on the y-axis here. That means that gravity is vertical. It is headed in a negative y-axis direction, so down. Down relative to whatever it is you're standing on. You can change that. And voila, you have x-axis gravity. Positive x-axis will be like that. So negative or positive, x, y, z, pretty self-explanatory at this point, but figured I'd show you anyway. This is the point where you shout at the screen and tell me I'm really boring. Anyhow, the next few sections are air density, wind speed, wind direction, and wind noise. Now, air density at a 1.0 basically simulates standard air density on Earth. Increasing or decreasing that will increase the density of the area around the particle through which it must move. So you can increase that or decrease that, and you'll have an effect similar to thicker or thinner air. Wind speed is just another way to add a wind effect to your particle. However, keep this in mind, any particle that is bound to this nucleus can have these same laws affecting it through this nucleus. If you were to create another end particle object and you wanted the same nucleus, you could do that. However, if you go back to the end particle and change things like wind and force in here, that will only affect the end particle object. So that's a pretty clear distinction. So if you want, like, I guess you'd call it worldwide or universal effects, use the nucleus. If you want single particle system effects, use that end particle. So anyway, we've got wind speed, which will apply another wind force like we talked about earlier. Wind direction will change that. And wind noise will add a measure of turbulence to that wind speed effect. Next section is the ground plane. Now, I appreciate this section because it allows for a lot of good testing to go on. Basically what this does, as you can see here, is it just creates a simulated ground plane, even if you've got no geometry in the scene at all. And it'll allow you to scale that up or down and modify it a little bit. I like it because it creates a nice ground plane there. And you can see that that's elevated. I believe that's just because we've increased the height since we spawned it. So, for example, if we increase this nucleus height, now you can see it's relative to that. But regardless of the odd offset that we're getting here, you can see that it provides us with a ground plane that we can use. And this will automatically apply collisions, and it will allow you to put together a number of different attributes here. The plane normal just designates the facing of the normal, which is to say the top surface of the plane. So you have it facing positive y, which means that the normal is going to be facing up on a vertical axis. You can change the axis however you like. Plane bounce. I can just show you this just so you understand what bouncing actually is. So you can see that slight bounce there. Let's increase that. And there you go. Plane friction will actually, again, do the opposite of bounce and sort of drag them to a halt there and make it extremely hard for them to traverse the surface based on the wind speed that we have applied. And plane stickiness, if I, for example, grab this ground plane, shift it, then apply some stickiness, you can see that despite the downhill slope, it all sticks directly where it lands. And you can lower that, and you can see it's got some slight movement to it, but it is still attempting to stick to the surface. Now that is independent of friction because you can see our friction has a 0 value. Now, the next section here we have is solver attributes. Now, these are a little bit esoteric, but basically they dictate the quality of your overall simulation in certain ways. Specifically, you have substeps, max collision iterations, collision layer range, and your timing output. Now, substeps are probably the most important of these, and it's basically the number of times this particular nucleus calculates per frame. You want, just as a rule of thumb, when working with substeps, you want more of them if your simulation is something fast or frequent, because you want to be able to capture it as many times per frame and calculate it as many times per frame as you can. However, that's not really necessary in terms of modification if your particle is a slower moving object. It just helps you increase the accuracy over time. Now, max collision iterations, we've been there before. We've seen that before. Essentially, that means how many times can a particle collide with anything, as opposed to just self-collision. How many times can it collide with something before it stops doing that? Now, that is nucleus-wide, so any end particle attached to that will have that same attribute. And then finally, you have collision layer range in terms of the important ones for today. Collision layer range basically determines how close two objects or particles within that nucleus have to be in order for them to collide with each other or interact. Currently, it's set to 4, which means that if an end particle or an end particle in an object or an object in an object are within 4 little units on this grid here, they can collide. Next here, we have the time attributes. Now here is where you can actually change the frame. Now remember back to the end particle where we can only see what the current time was and what the starting frame was. Here is where you can change the starting frame for your simulation. I find this pretty useful because I like to go back when beginning a simulation. I like to go in and set this to a certain negative value so that when you're rendering stuff out, you can still start on frame 1 and get the full benefit of your particles without having to sort of rev them up or generate particles beforehand, and you can do that in the negative frames. So I like setting this to something like negative 40, letting it generate for 40 frames, and then letting it loose. So next you have the scale attributes. Here you have time scale and space scale. They're both set to a 1.0 because that's a 1-to-1 ratio in terms of how many seconds pass to how much action takes place in those seconds. And over time, or over movement through space, how much spatial movement is taking place. Basically, it lets you set relative time and relative space. When you modify these, you're essentially saying an object is going to move faster over time than it should, or slower over time than it should if you're using the time scale. And if you're using the space scale, with an end particle object or an end cloth, if you ever get to using some end cloth, it applies a force with a greater scale over time that moves it through space, or a lesser scale. So if you'd like to scale that at any point, you can do so here. So that's about it for the nucleus. And as we're done with the nucleus, that is it for the 3 main sections of your end particle. You have the emitter, which, let me remind you, covers what happens to the particles as they spawn and how they spawn. The end particle itself, which covers what a particle acts like and is influenced by after it spawns and interacts with the environment. And the nucleus, which can set the physics and the general interaction with the surrounding environment. Those 3 make up the particles in Maya. That's really it. Now, that might seem a little bit trivial and a little bit simple, but what brings you to a more complicated area is when you attempt to do something specific, like create a torch or create a waterfall or something like that. And when you do that, oftentimes you do that for the first time, you're going to be using a tutorial. And what's going to happen is you're going to adjust each and every one of these settings based specifically around your goal, and then tweak them. Tweak them and tweak them some more. That's probably the most important part of building a particle system, is knowing where and what to tweak in order to achieve your desired effect. And that is probably the main reason why I give you this primer today. Knowing what each and every one of these does for the sake of tweaking those particles when you're approaching a certain goal or certain effect or certain look. You need to know what all of these do. So I just figured I'd give you this basic lesson, and from here you can go forward with a basic knowledge of each of these sections. So anyway, thanks very much for watching. Look forward to more lessons at the Colgate Viz Lab, and enjoy your work.